Okay, so we need to think a little bit more about how water is getting to the plant and then moving through the plant. So if you think about it, kind of makes sense that plant isn't at the total mercy of its surroundings in the sense of if water just happens to trickle by, I can capture some. That's not really what's going on. The plant actually has a mechanism in play that can allow for water to be directly moving toward the plant roots in the soil by their actions. So they create a situation that allows for positive water flow toward their roots. So they're not just sitting there at the mercy of, oh, I just hope a rain event comes along and water happens to come by my roots as it rains down on the soil. That's not what's happening. I mean, that helps, but they have the ability to direct the movement of water from further away from them to their roots. And so they're not as helpless as you may think. And so here we looked at this last time, how the plant is actively taking up water from its roots. And then as that's happening, you have to imagine that the soil particles are losing, the soil system is losing water. And so that you get this, first the water from the bulk area of the water in the soil is taken up. That's the easiest to get access to. But as that happens, you get more of just the water left over that's clinging to the soil particles. That's a little tougher to get access to because of cohesion forces. So water is like, oh, I like to hug this soil particle, and it's a little harder to get access to that. So there has to be a way for the plants to develop a force in order to keep getting that positive water movement toward them. So we went over this last time, how you have to remember that water has a high surface tension. So at the air water interface, you have a really quite decent surface tension. And so as you get the water drawn away from the bulk water in the soil, you're left with receding water molecules into tighter crevices and cracks and nooks and crannies. And what that does is it creates that curvature of the meniscus. And so when you have that, it actually does really put a nice tension force with smaller and smaller radii of the curvature of the meniscus, or the menisci for plural. And so this is something that you can actually mathematically calculate. So this simple equation, psi sub p is equal to negative 2t divided by r. We went through this last time, how if you know that the surface tension of water, that's a known value, you can plug in. And then if you play with the different radii of the menisci, and depending how big that value is or how small that value is, you can start to see how it impacts psi sub p. And it's negative, of course. Okay, so tension is negative pressure, so you have a negative sign. And so if you plug in, here you're looking at water evaporating off, or you can imagine, in the case of the roots, they're taking the water into their roots. And so that soil water is getting depleted. And so you get the liquid molecules that are clinging on to the soil particles, and you start to get more, the radii get smaller and smaller and smaller as that process is going on. And you end up with some really quite negative tension forces. And so what's happening in the soil system is you got to get that, where did it go? You have to get that tension gradient developed. And so by the roots near there, in that part of the soil system, you get a pretty decent tension. And then there's less tension further away from the root. And so as long as the plant can maintain a gradient like that, you'll have movement of water, liquid water, through the soil system. all the way to the roots. So remember now, the water potential in the soil, we said you can kind of just basically ignore Sisab-S. That's something that plant physiologists are happy to do. And so really what we're seeing here is the only component for the water potential equation is, I keep losing the W. That's weird. Is the Sisab-P value. And so you can also say, you could also state it this way, water will move from a less negative water potential in the bulk soil to a more negative water potential near the roots. You can say it that way too, and that's totally fine. But you need to understand it's really a tension gradient that you got going on here in the soil system. In the soil, we just pretty much say, let's ignore Sisab-S, it's such a small value. We'll just focus on Sisab-P. So in this case, Sisab-W is equal to Sisab-P. And that's going to be a negative value because it's tension. Make sense? Okay. So we went through that last time. Then we started thinking about the idea that, okay, the roots are taking up that water, and the plant physiologist said, there's probably 3 different routes that water can take once it gets taken up by the root hairs and gets into the bulk root tissue. So there's 3 different ways. Do you remember which way is probably the most common strategy for the plant? Look in your notes if you don't have it in your head. What are the 3 different routes or in the PowerPoint? Well, what's the one, you don't have to say the 3 different routes. What's the one that they think is the way that water moves in the plant tissue? Apoplasm. So they think it's that because it's the most efficient way. You just have the water skirting around in the cell wall space. And that's actually pretty efficient. There's no cytoplasm to get in the way. It just can skirt around and get through that bulk tissue of the roots. This is all pretty much just parenchyma cells that it's flowing around. And then it gets into the core area of the root in this case. And it needs to get to the xylem cells, which are in that cross configuration there. And so once that water gets dumped into the xylem, the tracheids and vessels, then it can just start, it's like an internal highway system. It just starts coursing up through the plant from trachid to trachid to trachid, all the way up to the leaves and the veins of the leaves. So we talked about last time, like, okay, they're trying to figure out how does that happen though? You have to have some kind of force being applied to get water to move up a plant body. And so they thought about the idea of positive pressure, which you can demonstrate by the guttation idea. On a morning after a cool, humid night, you often have dew on the grass in your lawn, or here, these are strawberry plants, which are also pretty petite plants. So that's what got them thinking, oh, maybe it's positive pressure pushing up, water's getting pushed up from the roots. But when they did all the calculations of the rate that they could see water moving through a plant, and then they calculated the diameter of the tracheids and vessels, and they started thinking about all that, they're like, yeah, that's not going to work. And so they had to pretty quickly get rid of that idea. And instead they went with the cohesion tension theory, which is kind of the opposite idea. Instead of water being pushed up the plant, it's getting pulled up the plant from the leaves area. That's where the force is actually getting generated. And so cohesion tension theory is the most accepted theory describing this phenomenon. And so cohesion is water molecules love to hang out with each other and bond with each other. So as long as you have a cohesive volume of water going through the xylem, this can work. Tension, the idea that it's under a tension force. All right. So we were thinking about this toward the end of last session, where we have a leaf and you have to imagine the vein. So they're showing the vein here in cross section with the xylem in red. And you have to imagine that there's water kind of oozing out of there, and it starts to coat or cling to the surfaces of the cells in here, particularly the spongy mesophyll cells or parenchyma cells. And then you have pretty analogous ideas to what we just described in the soil system. If you just kind of replace soil particles with spongy parenchyma and palisade parenchyma, you kind of have the same idea, where you have that liquid water clinging to the surface of these parenchyma cells, and then you get evaporation going on into all this airspace here. So you have liquid water getting converted to gaseous water vapor. And then they're trying to show with this blue line here that the water vapor is exiting out of the leaf because the stomata are open. So if the stomata are open, yep, you got water vapor exiting the leaf. So if you imagine that happening over and over and over and over again, you can imagine where the water molecules start to recede into smaller and smaller spaces as more water is exiting out of the leaf. And so again, you get that idea of the curved menisci that are forming in the nooks and crannies of the spongy parenchyma cells. And so again, if you have that situation where you get some pretty decent small radii here, then you can see how that's generating a tension force on all those liquid molecules, water molecules. And they say that as long as all those liquid water molecules are cohering with each other, they're bonded with each other, and as long as it's like a solid column of water from the vein in the leaf all the way down to the roots, as long as it's a solid column, you're going to feel that tension force all the way down to the roots. So they're saying that up in the leaves, you get a pretty decent negative Sisa P, pretty decent tension force there. And you talk about a gradient again. We're down at the roots. It's not quite such a strong tension force. So you get a gradient. And again, you'll end up with water moving from, when you think about water potential, it'll be less negative water potential down by the roots and more negative because of that nice tension force up in the leaves, more negative water potential up by the leaves in the veins. So again, we go back to this image again. And in this case, when they say evaporation, they're really zooming into what's happening in the leaf. They're saying the liquid is converting into gaseous water vapor. And as that keeps happening over and over and over and over and over, you get the receding of the liquid molecules into tighter and tighter spaces. The radii gets smaller and smaller. Your tension gets really quite negative. You get a negative Sisa P. So they're trying to show that here too. This is showing 3 different radii that they're saying, you know, as you have that evaporation going on, you get that smaller and smaller radii. So pretty similar to what we saw in the soil, don't you think? Okay. So transpiration is a process. And some students in the past have asked, well, what kind of essay questions do you ask? This would be a good idea, right? Because it's a process. I could ask you some multiple choice on it too, but describing processes in this type of class, those are decent essay questions. So what we just worked through as a group, this might be something we'll ask you to type up on the exam. Explaining, not just saying, yeah, it's a tension force. You need to explain to me, okay, well, how does it develop? Where is it originating? Like, what's kicking it off? How does it develop? And then how does water move? So basically what we just went through is, you know, it's a big deal. How water moves through the plant body. This took plant physiologists a decent amount of time to try to figure out. And this is the most widely accepted, and they call it a theory now. It's not just a hypothesis. So pretty important process for you to understand about plant physiology. So let's think a little bit more about it. If you are thinking about, so transpiration, when you say that word, it's the movement of water through the plant body. That's what they're talking about. And ultimately, it's going to be exiting out of the leaves, out of the plant body through the leaf stomata. So this, they had to think about, well, what's kicking it off? Like, how does this even start? And they had to go back to the leaves. That's where they had to go to figure this out. Because they fairly quickly realized that in order for water to move through the plant body, you have to have the stomata open. Otherwise, it's not gonna happen. So the stomata must be open in order for transpiration to kick off. So let's go back to that leaf picture. Okay, so here you're seeing the stomata open. And they're showing this blue squiggle line, that's the water vapor molecules coming out. So if you close down those stomata, the water vapor will be in the leaf air spaces, but it's not going anywhere. It's just sitting there. So there's no tension force starting to kick off here if you have a stomata closed. You'll get no tension being generated here. So you won't have any water movement up through the plant body. So around here, in this part of the world, most of the plants that you look at that are native to the area, pretty much all of them, they typically close their stomata at night because the sun goes down. They can't do photosynthesis without sunlight. So why bother keeping your stomata open at night when you don't need to take in carbon dioxide for photosynthesis? It's like, why should I keep my stomata open? It doesn't make sense. You have to realize those stomata, by the way, when you open your stomata, you're opening yourself up to potential pathogens getting in. Fungi can get in, bacteria can get in, viruses can get in. Those pesky insects with those really thin stylets, mouthpieces, they can do some damage. So it would be kind of smart, like if I can't take in, if I can't do photosynthesis, I don't need to take in CO2, I'll just close my stomata because it's a risk having my stomata open. The other idea too is if I have my stomata open, I'm losing water. It's automatic. A plant can't say, okay, I'm going to open my stomata, CO2, come in. Oh, but water, you got to stay here. You got to stay in me. It doesn't happen. It's kind of like secondhand smoke in a restaurant. You can't like put a imaginary divider in the air and say, this place is non-smoking and right next door is smoking. You're going to get the smoke everywhere. So it's kind of, you open the stomata. As soon as you open the stomata, you have water vapor exiting. Plants cannot control that. The only way they can stop it is to close their stomata. So there's a lot of good reasons to close your stomata during the night to plants that are native to these types of environments. Okay, so stomata have to be open in order for this tension gradient to start happening. So as the stomata open up, you have water vapor exiting. And so that's evaporation going on. You have the liquid water going into the gaseous state and then coming out of the leaf. So that starts to happen. And that is really what's then kicking off this idea that you'll have the liquid water in the leaf receding into the smaller and smaller cracks and crevices so that the radii get smaller and smaller and you get that nice negative psi sub p. Okay, so really, the stomata must be open. That's what really kicks it all off. If you don't have that, you don't have transpiration. So to get nitpicky about it, really, it's not just that you have tension up in the leaf. That's not the complete story. To finish the story, you have to talk about the idea that down in the roots, let's say, you have less tension. And so you have a less negative psi sub p down there. And so you have a gradient. Think about gradients when you think about movement in this class. You have to think about gradients. And so you have to finish the story and say, well, okay, we got to get some kind of tension gradient down in the roots. It's not going to be as strong. And so you will get that gradient. And so if you have, if you can explain how water is moving through the xylem and it's pretty much through Sisa P, you have a gradient with Sisa P, a difference of Sisa P from the roots to the leaves, that's bulk flow. We're talking about bulk flow. So that's a Poisson equation that we introduced the other week. And so this is the idea that you have movement of water through the plant body due to a tension gradient. And you have to have the understanding that it's unidirectional. Once water gets into the xylem down in the roots, it's one-way transport. You don't have water in the xylem up in the leaf going down to the roots. That they've never demonstrated that. It's always roots, stem, branches, veins in the leaf, out to the stomata. And that's pretty much it. Unidirectional. So water is pretty good at clinging to other water molecules. So that cohesion force is pretty decent. And if we had pure water moving through the plant body, it would be really nice tension gradients. Everything would go along quite well. Is water that's found in the soil, is it pure? Pure water? No. So now we got a conundrum. All right, so we don't have pure water. We have, ideally, lots of lovely minerals dissolved in the water that the plant is taking up, not just water, but all the dissolved minerals that it needs. So we can pop a multivitamin for our minerals, or we can get it from good food. Plants get their minerals from the soil and the processes of what's going on in the soil. Okay, so there's minerals, but you also have to appreciate there's dissolved gases in the water as well. There's dissolved, pretty much the air that we're breathing right now, that's in the soil. You have oxygen down there and nitrogen and CO2, and you have some other interesting gases that are being produced by primarily by microbes. So they like to produce, some produce methane, some produce hydrogen sulfide, ammonia, nitrous oxide. There's all kinds of stuff going on. So there's dissolved gases in the water. And if you've ever taken a physics class where they give you a beaker of water with dissolved gases, and then you start putting that under a tension force, where you kind of pull on that column of water, so to speak, you put a tension force. If you've ever watched that, it pops the bubbles out of solution and you can actually see the bubbles. It's kind of like cracking your pop bottle for the first time and you see all those bubbles rushing. It's kind of that idea. They come out of solution once that pressure's been released, tension. And so that can be not so good for the plant body in terms of water movement, because what happens then, so this is what should be going on. You have liquid water coursing through the xylem. Remember, xylem is clustered. You have clusters of tracheids and vessels all clustered together, and they share pores between them so that you have the opportunity for water to go from neighboring tracheids to a neighbor trachid, for example. You could do that. Here they're showing really nice flow of water. Everything's going along good. Now in this image, they're showing gases coming out of solution. So it'd be analogous kind of to getting an embolism in your blood vessel. And if you know anything about that, is that a good thing? No, it can kill you. It won't kill the plant to have this happen, but it could if it happened all at once, but that we don't see that happening. So here you see vessels and tracheids with air bubbles. So the white area is demonstrating that a big air bubble came out of solution. Maybe it's CO2 or I don't know, some kind of gas that came out of solution. And what they're trying to show here is now you've interrupted that column of water. So that if you look down here, they're showing how the water needs to reroute. Water can't go through that air bubble. It won't go. It's stuck. So it's rerouting. So that's an excellent reason and an excellent evolutionary strategy for plants to have clusters of tracheids and clusters of vessels. Because this happens every year. They have to face this every year. This happens to them. And so rerouting is a good idea. They show it with the tracheids too, how that big air bubble, gas filled cavity, and it's rerouting. So the fancy word for that is this cavitated. They call it cavitation is the fancy word. We don't say embolism. We replace that with cavitation. So cavitation occurred. That's what you're seeing here. So now that particular vessel and trachea that has that big air bubble, it's toast unless that air bubble can be put back into solution and get redissolved. Unless that can happen somehow, that whole highway system is toast. Which do you think would be easier to get back into solution? The air bubble that you see here in the vessel or in the trachea? If there could be some kind of force applied, which do you think would be easier to get back into solution? The one in the vessel or the one in the tracheids? It's actually the tracheids. Yeah, it's so, because you have a smaller space here, narrower diameter, the physics of that actually makes it a little easier for that one to go back into solution. Vessels, this is a little bit more of a luminous air bubble, I guess, and a little tougher to get all of that back into solution. So vessels, angiosperms. So we consider the flowering plants, the angiosperms, the most advanced plants on the face of the earth. They're sophisticated in many ways, and they point to vessels as being one of the adaptations that angiosperms developed that really gave them an edge. Here's a downside to it. Okay, so here we're pointing out a downside. The downside is if you get an air bubble coming out of solution in vessels, it can be tricky to get that to go back into solution and then become a functional vessel again, where water can course through cohesive forces. So by the end of the growing season, around now, a lot of angiosperms trees that are out here right now, they have a lot of cavitated vessels that are just toast. They're useless. So thank goodness they have a lot of vessels, and angiosperms, they hedge their bets. They lay down vessels because that gives them an edge, but they also lay down quite a bit of tracheids. And in fact, they're quite dynamic. In the spring, angiosperms go, all this in this area of the world to go, oh, lovely snow melt. I'm getting all this water from snow melt in the soil, all the rain events due to spring. I got all this water. I'm just living high on the hog here. So they'll lay down a lot of vessels because it's very, very efficient. So they'll do that first in the growing season. And you can see this if you take a cross section of a tree trunk and look, you'll see a bunch of vessels during the spring growth season. Then as summer wears on and drought starts to pop up more and more, they can sense that. And so as they're growing, they'll go, yeah, I'm going to do tracheids now. I'm going to do that. I'm going to do more tracheids than vessels, because if I run into cavitation, it's going to be a little easier to deal with. And I won't have so many dead spots, so to speak, where I won't have active water flowing through. So they're that sophisticated where they can decide, so to speak, based on environmental cues that they're sensing, of whether they should build vessels or tracheids as they're growing through the growing season. So if a tension force generated these air bubbles to come out of solution, what would be a way to get them back into solution? Put your physics hat on. If tension generated an air bubble, how would you try to get the air bubble back into solution? Pressure, positive pressure. So a plant can't really do positive pressure per se itself, but one thing they can rely on. So around here, I just said a little bit ago, stomata close at night, right? So if they close their stomata at night, that releases the tension on the water column in the vessel and the tracheids. So if you get that release, that's sometimes enough to get those bubbles slowly to go back into solution through the night. So, and that does happen. And then luckily they have, through the evolutionary process, they cluster their vessels and tracheids. So if necessary, they'll just keep rerouting the water to a neighbor. So this can be a big deal. By the end of the growing season, they tend to think that a lot of vessels are not working anymore for water transport. They're good for structural support, but they're not doing a ton of water transport. The tracheids tend to take over with the angiosperms. Going back up to the leaf, again, looking at, there's a variety of designs of stomata, but no matter what kind of stomata you have some kind of guard cell guarding the pore. Figure C here, you can see that these kidney-shaped guard cells are allowing for quite a wide pore. And then the figure B, you see they kind of look like the dumbbell-shaped guard cells. Okay, so the guard cells are guarding the pore. And so it looks like it's kind of hard to see with figure B, but I think figure C, even from where you're sitting in the back, you can see that there's some chloroplasts floating around in the guard cells, all the green stuff. And so they studied a lot of different guard cells, and because they knew stomata have to be open for transpiration. So they really started to hone in on, okay, how do guard cells function? What's allowing them to open or close? What's the process of that? Because they recognized how important this is for the plant. And so when they saw that there was a bunch of chloroplasts in the, some of these guard cells, they started thinking about the idea of osmosis and how, water is either rushing into the guard cells or out of the guard cells. And we talked about this a little bit when we were looking at plant anatomy. No matter what shape your guard cells are, they discovered that there's these microfibrils, those black lines are the microfibrils, and they're laid down in such a pattern in the cell wall that it allows for, once those cells get full of water pressure, it causes the guard cells to bend away from each other. So if my hands are the two guard cells and the pore is closed right now, water rushes in and it causes this bending force away from each other, and that reveals the pore. And so it's just the radial alignment of those microfibrils that's causing that. So they figured that out pretty quick through microscopy work. And they realized that, it doesn't always have to be 100% open. They can vary how open that pore is, and they're pretty good at that based on sensing how much water they have access to. And so they started studying a lot of different plants, looking at a bunch of different stomata from these different species. And they had to come up with an idea of, how is water rushing in or out? And they thought, well, okay, we need to think about the laws of osmosis, because these guard cells have, cell walls and cell membranes. So water is passing across a membrane. And so that's osmosis. And so they started thinking about, okay, well, but the plant's got to have a mechanism in play to kind of control that process. And how are they doing that? So that's the next thing I want to talk about. But basically, by the time they started piecing this all together, they definitely saw that stomata must be open. That's the first thing that has to happen. And as soon as you open the stomata, you get evaporation of water vapor out. You can't stop it. So that starts happening and creates a nice tension force up in the leaves. And as long as you have continuous water, liquid water, all in a bulk system, all the way down to the roots, you'll have that gradient of nice negative pressure up in the leaves, a good tension up in the leaves, less further down. And so you have that gradient, which will allow for the water movement, unidirectional from the roots up to the leaf veins and out through the stomata. So here you're seeing different water potential values, just to show you down in the soil, you have less negative water potential, and then as you get further and further up, you get more negative. So we are following the laws of water potential, less negative to more negative is how water will move. And eventually you'll get up into the veins of the leaf and you will get the liquid water going into the gaseous state and exiting out of the leaf. So they realize that, the plant, different plants, of course, have different habitats and different environmental parameters that they have to deal with. And so they started thinking about, well, some plants seem to have very fast transpiration rates, others not so fast. What kinds of things are impacting that? So we're going back here to the leaf. And one thing I want you to pay attention to for this idea, well, do they have it on here? Not really. Okay. So it's important to realize that they just say high water vapor inside the leaf. When they actually do measurements, it's pretty much 100% relative humidity inside the leaf. So the relative humidity, I find it a little bit easier to think about what's going on if I think about relative humidity for this particular idea. So inside the leaf, they say it's pretty close to 100%, just a touch under that. So plant physiologists said, let's just call it 100% in the leaf. So basically, the air spaces in the leaf are fully saturated with water vapor. So relative humidity 100%. So then if you think about different days of the year that the plant is experiencing, of course, just by living your life, that relative humidity from day to day can vary. It can be super humid some days, other days not so humid. And so now we need to think about a gradient again, in this case of relative humidity. If we want to think about how fast is that plant going to be doing the process of transpiration, how slow is it going to go? So if you have 100% relative humidity in the leaf, and then let's say there's a day of 75% relative humidity, and then there's another day, the next day it dropped down to 40% relative humidity. So day, let's say A and day B, two different scenarios, A and B. So which would give you what I like to think of like a shallow gradient of relative humidity or a steep gradient? Which one would be a steeper gradient, A or B? From 100% to 75% or 100% down to 40%, which is a steeper, greater gradient? Yeah, figure B, 40%. Example B. So that's a bigger difference, 100 to 40 or 100 to 75. Well, 100 to 40, that's a bigger difference. So a steeper gradient is another way to say it. So if a plant is surrounded by 40% relative humidity in the air, it's going to transpire faster than the same exact plant that's at 75%. It's very analogous to you in the summer. If you are sweating, if I make you run a 5K race, and then I put you into a grow room that's 75%, and I put somebody else at 40%, the person that's sitting in the 40% room is going to be sweating quicker, losing that, evaporating the sweat off their body quicker than if they were stuck in the 75. So think about sweating and use that analogy for what a plant is doing in terms of the transpiration rate. And so the fancy way to talk about that is you can also think about the water vapor concentration inside the leaf, which is, again, it's like 100 versus what's going on out in the air. You can think of it that way too. It's equivalent, relative humidity and water vapor concentration. For this purposes, you can just think of it as an equivalent idea. And so you can either say a relative humidity gradient or a concentration gradient. And so again, that's steep versus shallow. I like to do, so here are some equations that I won't ask you to, that V sub W should be under there. I don't know what happened. I won't ask you to calculate. I'm not going to, have you do any of that. It's more of a thought idea of, different humidities. How would a plant transpiration rate differ under different humidities, and you don't have to do any calculations, just think about it. Use your own sweat on your body as an example of how would you cool down quicker in which scenario. So you can measure relative humidity in the leaf. So the inner air spaces, you can see it's at 99%. So they just say, yeah, let's round up to 100 and call it good. So you can measure relative humidities in the leaf and outside. Water vapor concentration. And then again, on the far column, you can see the water potential. And again, it's going from less negative in the leaf, inside the leaf, less negative water potential to more negative outside the leaf. So again, you're still following the laws of water potential gradients or water potential, where we know water moves from less negative water potential to more negative water potential. Okay, so that's still a thing. Does that kind of make sense? So use, if you have if you've really developed a sweat and you think about what makes you cool down and have the sweat evaporate off you quicker under what humidities, that's a good analogy. The other thing I want you to pick up on, let's go to this one. Where'd it go? This image here is, I don't know if I pointed this out at any point, but this kind of tannish squiggle that they've drawn on the top of the leaf and the bottom of the leaf, that's not, in this case, it's not the cuticle. What they've drawn there is what they're labeling down here, the boundary layer. So the boundary layer, the air boundary layer, what this is trying to show is that when you have a solid surface and then the air, bulk air around it, there's a very thin layer of relatively unstirred air, relatively still air molecules right at the surface of that physical substance compared to the bulk air above it. The bulk air above it, the air molecules are moving much more than the layer of air molecules right at the physical surface. So you have a boundary layer, you have an air boundary layer, you're a physical thing, a wonderful thing. And so all on your body, you have a boundary layer, an air boundary layer. And it can be, it can vary a little bit in its thickness. So if you were a twin and I put your twin in a room that had a wind coursing along, first I made you run a 5K race, you're all sweaty. And then I put your twin into a room that has no wind. And I put you into a room that has a 20 mile per hour wind. Who's going to cool down faster? Wind or no wind? Wind, right? I mean, I think you've lived your life long enough. You get the basics of that idea. So, okay, but why? What's happening is that boundary layer with the wind is thinning way down. You've stirred up a lot of these air molecules. So your boundary layer is super thin. Whereas your twin that got into a room with no wind, the boundary layer is still pretty thick, relatively thick. And so if you have conditions that thin out that boundary layer, you're going to have faster transpiration rates. It's easier. These little squiggles, by the way, on the blue line, that's frictional forces. And still air creates more friction than stirred up air. It's moving around like crazy. Then you won't have such a squiggly, so much frictional forces. So thinning out that boundary layer is going to allow for faster transpiration rates. And so they did a lot of measurements and tests with this, and they were definitely able to show, the fancy way to say it is that it modifies the length of the diffusion path of the water vapor molecules. Basically, you're just thinning out the boundary layer with increasing wind. Now, plants have physical ways to kind of manipulate that in a way by how they adapt to their environment. They can change their leaf size to some extent, their shape. They can actually modify how many leaf hairs they have. And if you've had BI 230, you know that leaf hairs are called trichomes. Okay, so the trichomes. So plants can modify how many leaf hairs they have. And if you have a bunch of leaf hairs sticking off the leaf, that in essence creates a pretty nice thick boundary layer. It helps keep the air molecules still. If you have all these hairs standing up on your leaf surface, you get a relatively still air there. And so that's a pretty thick boundary layer. So if you find a plant that you want to have in your apartment or dorm room or whatever, and it's got a lot of leaf hairs on it, a lot of trichomes, it's probably a plant adapted to pretty like dry conditions, desert conditions perhaps, or just dryish conditions where they have to have a thicker boundary layer to kind of slow down transpiration, because they probably are faced with an environment that water is not super abundant. And so they really kind of slow down their transpiration. Leaf size as well. If you have a smaller leaf, you can slow down your transpiration in general, smaller leaves. So if you think about succulent plants, and like some succulents don't even have leaves, like giant saguaro cacti, they don't have leaves. They just have tree trunk or a trunk. So leaf size in general, smaller, it helps you slow down your transpiration. I'll talk a little bit more about shape. And then stomata location. So if you look at certain leaves, some leaves have stomata on both sides of their leaves. Some leaves have stomata only on one side. And again, that's not a mistake. That was a process that was done through adaptation to their environment. Oh, let me finish this equation. So this is going back to that, how long does it take for something to diffuse? The distance squared, K over D, you've seen that equation before. So again, just showing that if you thin out that boundary layer, it messes with your distance value. And that can, if you thin out your boundary layer, you increase your transpiration rate. So plants are not just sitting there at the mercy of their environment and everything around them. And they have the ability in real time to manipulate things, also through just adaptation through the generations of them living there. They can adapt to their environment. They can create situations that allows for positive water flow. So they're not just sitting there like what a lot of people think when they look at a plant. Oh, it's just sitting there. There's so much going on that it has control on, and then they have exquisite ability to adapt to their environment. Sometimes within a single lifetime, you can see them adapt. For example, their leaf size and shape. One tree, for example, can have different leaf sizes and thicknesses. And so they have a lot more control on what's going on with their body and with their physiology than most people realize. But we'll stop there and we'll finish off this idea. And then we have to get into phloem translocation, how sugar moves through the plant body.